Hello and welcome. In this video we'll be learning about number bases, specifically those other than the decimal or base 10 system with which most of us are familiar. We'll take a particular look at the binary, octal and hexadecimal number systems. First, a quick recap. In the previous video we learned about how our numeral system developed. We learned about the concept of a positional value numeral system and why this kind of system is very useful in performing arithmetic operations, especially when working with large numbers. In this video, I'll cover the concept of a number system's base, or the number of symbols called digits which are available to put in each position, the specific cases of decimal, hexadecimal, octal, and binary, and a little bit of counting in each of these to show the workings of them. Remember that each of these systems are positional number systems. The number system that we use most frequently is called decimal. That means that the base of the number system is 10. There are 10 symbols available for us to use. The symbols are 0 to 9 and are used in various combinations to represent numbers. There is no specific reason that 10 is privileged other than that we have 10 fingers. This is the general theory. There have been a few cultures in the world which have used other number bases, but these have been comparatively few. These other number bases are, however, just as valid. In fact, any positive integer other than 1 is a perfectly good base of a number system. Unary numerals, which I discussed in the previous video, can in a sense be thought of as base 1 system, but this is a bit of an exceptional case, because unary does not follow most of the rules which apply to other number bases, which we'll look at today. As an example and demonstration of an interesting alternative base, I highly recommend Numberphile's excellent video on the Dozenal or base 12 number system. Now, some other bases, while being mathematically equivalent, may have specific advantages over others. For example, Dozenal enables easier fractions for many common ways of dividing numbers, as explained by Dr. Grimes in the Numberphile video that I pointed to. Easier fractions, and in fact easier multiplication, would certainly be a great gift to many struggling children in school, and many adults too. Another example is binary, or base 2, which has the very important advantage of being easy to represent in electronics. Octal or base 8 and hexadecimal or base 16 are often used because they make very useful shorthand for representing binary. It is for this reason that we will focus on these three number systems. I'm going to take a moment to mention two things which I think are relevant. In a typical digital systems course, the lecturer will often at this point teach, assign, and test his students in operations on numbers involving various arbitrary bases, such as 3, 7, 14, etc., while deliberately avoiding binary, octal, and hexadecimal. This is done so that the students can convert between these bases, often using decimal as an intermediate step, without the aid of a calculator. This kind of makes sense, as then the lecturer can easily determine whether or not the students really grasp the concept of numbers in different bases, before moving on and progressing through the powers of 2 bases that we'll talk about today at a relatively fast speed. I will do another video on arbitrary bases, but I think that this should be for interest only, as it doesn't really have much relevance in digital systems, and the general concepts can be easily learned when talking about binary, octal, and hexadecimal. If you are a student in a course where you find yourself in such a situation, please just be patient. You'll get through it and you'll be able to move on to more interesting stuff soon. The second thing that I want to mention is a word on nomenclature. Strictly speaking, it's not correct to talk about binary numbers or octal numbers. We do this just to simplify things and to make it a bit easier to say, but it's important to understand that numbers in binary are not different from numbers in decimal or any other base. 0110 in base 2 represents the same number as 6 in base 10. The number 6 doesn't care which base you represent it in, and it still has the same properties. It's 1 more than 5, it's divisible by 1, 2, 3, and 6, and it's still a factor of 12 and 18. If one wants to be very accurate, one would refer to 0110 base 2 as a number represented in binary rather than just as a binary number. But people very seldom do this because it's clumsy. In my case, I prefer just to state the base as I have been doing, 0110 base 2. This doesn't make a great deal of practical difference, it's just something of which the diligent student should be aware. To demonstrate the basic concept of how these number systems work, I'm going to do a little bit of counting in each one. Since we already have an intuitive understanding of how decimal numbers work, I'll have the same example represented in decimal alongside, so that we can see how the number systems work compared to each other. Decimal uses the symbols 0 to 9, while hexadecimal, by convention, uses the same 0 to 9, but with the addition of A to F. Let's start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now we've run out of digits in decimal. In hexadecimal we're still fine, we can use the next symbol, A. To go any further in decimal, we need to make use of a property of positional number systems. When we have only one position, that position represents units. To go on from this, we add a second position, and this represents the base of the number system to the power of 1, in this case tens. So we reset the number of units to 0, and in front we add a 1 to represent 1 times 10. So 10 in decimal is A in hexadecimal. Why have I taken such pains to point this out? Well, it's something that we see so often when we are counting that we don't stop to think about why it is the way it is, and how this principle can be applied more generally. We'll see how it applies in hexadecimal in just a moment. Carrying on then as normal, we get to 11 or B, 12 or C, 13 or D, 14 or E, 15 or F, and then we get to the same problem in hexadecimal that we encountered just earlier in decimal. Just as with one digit in base 10, you can represent the numbers 0 to 9, with one digit in base 16, you can represent from 0 up to 15. 16 in hexadecimal then becomes 10. And so it goes upwards through the numbers until you get to 19 in hexadecimal, which is 25 or 25 in decimal. Now there's a temptation to forget, if you're trying to count in hexadecimal, to go from 19 to 20 as we do in decimal. But in fact, you need to go to 1A or 26 in decimal, then 1B, 1C, and so on until 1F in hexadecimal. 1F in hexadecimal is 31 in decimal, or 31. Just as before, we reset the units column and increment the 16s column, so the next number is 20. 2 16s, 0 units. This means 32, a number that we can easily recognize when written in decimal. If you recognize and remember the powers of 2, then you'll begin to anticipate how useful this can be. Let's try the same exercise in octal or base 8. 1, 2, 3, 4, 5, 6, 7, and now we've run out of octal digits, so we need to reset the units to 0 and increment the 8s. So we have 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, and following the same pattern again, 2 0. 2 8s, 0 1s, which we can recognize quite easily as 16 in decimal. Let's count a bit in binary as well. 0, 1, and already we've run out of binary digits. So we follow the same pattern, reset the units to 0 and increment the 2s. So we have 1 0, 1 1, and we've run out of digits again. Now this can be rather tiring. No matter, we'll carry on with the new column. Reset the units column, increment the 2s, but the 2s column is also full. So we'll reset that as well and increment the 4s column. So we have 1 0 0. And the pattern continues, 1 0 1, 1 1 0, 1 1 1, and we're now at all 1s again, so to go any further, all of them go to 0, and a new column gets added, 18, 04s, 02s, and 0 units. 8. As an aside, binary representations tend to be on average about 3 times longer than decimal if you write them out, but this is very easily dealt with by very large-scale miniaturization in electronics. We'll get to that a little bit further along in the course. And that brings us to the end of this video. Quick recap. In this video we've learned about the concept of a number system's base, the number of digits that it has available for writing the number out. We've learned about the specific case of decimal, hexadecimal, octal, and binary, or base 10, base 16, base 8, and base 2. And we've done some counting in each of these, making use of the rules of positional number systems to move up through the numbers one at a time, simply lengthening the numbers by one place when we run out of digits. In the next video, I'm going to start talking about converting between these 4 bases. The biggest challenge is getting from decimal to any of the others and reverse. Once you have that done, then converting between hexadecimal, decimal, and octal is really very easy. And finally, I thought I'd leave you with a bad joke just to finish the video. Why do digital engineers get confused between Christmas and Halloween? Because 25 dec is equal to 31 oct.